Welcome to an introduction to linearization. This is a skill that we are going to use in almost every lab that we do in order to find the relationship between the two variables that we are working with. This is also something that's on the AP exam and will be on your tests and quizzes. So let's say that we have a graph, and our graph is a graph of velocity in meters per second versus time in seconds. And our graph gives us a straight line. You should know that a straight line follows the form of y equals mx plus b. So this is the form of the equation. Now in physics, we're not going to have y and x on our axes. We're going to have whatever variable we had data for in our lab. So if we have velocity data and time data, your independent variable is going to go on your x-axis and your dependent variable is going to go on your y-axis. So y equals mx plus b shows the form of a linear relationship. That's telling us that if you take your independent variable and you multiply it by a constant, which is the slope, and then add the y-intercept, you will get the dependent variable. If we were to write this equation in physics class, instead of having a y here, we're going to use a v because that's the variable that we're using. So we're going to replace the y with whatever's on our y-axis. And then we're also going to include the units. So we're going to put the units in parentheses behind our variable. Then we're going to put our slope in. So let's say that our slope here is 5. We're going to put that number in there. Now you need to include the units of the slope as well. To determine the units of the slope, you are just going to think about how you calculated the slope. So you figured out the slope by doing a change in y over a change in x. So you do the units on the y-axis divided by the units on the x-axis. So in this case, it is meters per second per second. So I'm going to put meters over seconds squared, and that's the unit of the slope. Meters over seconds squared. Then I'm going to multiply by my independent variable, which is on my x-axis, and that is time. And then we put the unit behind that. Then we add our y-intercept, so maybe this is 3, and then the unit of the y-intercept. So this is the equation of this line. Now, this would be the equation that's specific to my data, but if I wanted to write a general equation, I would replace the slope with the meaning of the slope, and I would replace the y-intercept with the meaning of the y-intercept. And the rate of change of velocity divided is change in velocity over change in time, and the units are meters per second squared, so that tells us that the meaning of the slope is acceleration. Additionally, the y-intercept here is the velocity at time equals 0, so this is our initial velocity. So our equation becomes velocity is equal to acceleration times time plus initial velocity. I'll write that a little bit not so stretched out. All right, so now what if you have a graph and that graph is not linear? How are you going to write the equation for it? We're going to use linearization to do that. So let's say that we are in thermodynamics and we have made a graph of pressure in newtons per meter squared versus volume in meters cubed. So once again, our independent variable is going to go on the x-axis, our dependent variable is going to go on the y-axis. And you have a curve that looks like this. If you were in math class and you saw this curve, you might say, oh, that looks like an inverse relationship. And it is an inverse relationship. So we can do something that's really slick. We see that this is an inverse relationship. So in an inverse relationship, we know that our pressure is going to be proportional to 1 over the volume. So we're going to graph pressure versus 1 over volume. we're going to take all of our data, our volume data, and we're going to take the inverse of it, and we're going to make a new graph. So we make that new graph. And pressure here. And it's going to give us a straight line. So we know that the equation of a straight line, the form of the equation of a straight line is y equals mx plus b. And we're going to replace the y with whatever's on our y-axis, so that will be pressure in newtons per meter squared. And then we have our slope, which is, we can just make up a number, let's just do 10. And we need to figure out what the units of that slope are. So like I said before, we're going to do units of the y-axis divided by units of the x-axis, because that's how you solve for the slope. So that would be newtons divided by meters squared divided by 1 over meters cubed. So when you divide by the reciprocal, or you multiply by the reciprocal, so we're going to multiply by meters cubed. So that gives us Newton times meter. So then that's the unit of our slope. And then we're going to multiply by our independent variable, which is whatever's on the x-axis, so that's 1 over v. And the unit of that is 1 over meters cubed. And in this case, we have no y-intercept. So you can put 0 if you want, or you can just leave it off. So what I've shown here is now pressure is equal to 10 times 1 over v. So this equation of this straight line is the same as the equation of this curve. So if you're in a situation using a program that does a curve fit, you could do a curve fit on this and you would get this equation. But if you're taking a test or you don't have access to that curve fitting technology, you can do this to figure out what the equation is. Now, let's try another one. There are 3 main shapes that you need to be familiar with in the beginning of this. So one is a hyperbola. The next one is a top opening parabola. So let's do one like that. So let's say you did another lab and you have something like position in meters on the y-axis and time on the x-axis. And you have something that's accelerating at a constant rate, so you get a curve that looks like this. Now, in math class, if you were to see this shape, you might say, oh, that's a parabola. And I know that a parabola follows the rule that y is proportional to x squared. And so what we're going to do is square all of our independent variable, or all of our independent values in our data table. And then we're going to regraph it. So we'll have position still here, and then we'll have time squared in seconds squared as our unit. And when we graph that, we're going to get a straight line. Now the units of the slope, let's say that our slope is 5, are going to be the units of the y-axis divided by the units of the x-axis, so that's meters over seconds squared. And now we can apply the same thing to find the equation. So y equals mx plus b. And replacing the y, I'm going to put whatever's on my y-axis, so that's position in meters. My slope is going to be 5 meters per second squared. And my my x is my independent variable, which is time squared. And the unit there is seconds squared. And then there is no y-intercept. So now this is the equation that shows the relationship between my 2 variables. There is a process for figuring out what the meaning of the slope is, and you're going to go through that and learn that with each lab that we do. I went through that process up here, but it's a little bit more challenging with those two. So you go through that process, but you learn that. later. All right, so we have our hyperbola, we have our top opening parabola, and the last one that you need to be familiar with, for right now, we will do more complicated linearizations later, is the side opening parabola. So let's say that we have a graph of position, let's do velocity and position. Okay, so we get a side opening parabola. So this is a square root function. So we're looking at a square root curve. So you might say, oh, that reminds me of y is proportional to the square root of x. And that's true. So you can actually linearize this one. Well, you can linearize all of them in several different ways, but you can definitely linearize this one by taking the square root of the independent variable and regraphing it, and you'll get a straight line. I think that gets pretty messy usually because then you get square roots in your units, and I don't really like that. So I prefer to square both sides of this, and then you get y squared is proportional to x. And when you graph that, you also get a straight line, but then you don't have the square root in the units, which is what I like to do. So I'm going to show you that one first. So we're going to make a graph of y squared, which is v squared, in meters squared over seconds squared, and position. And we're going to get a straight line because this relationship shows us that y squared, the dependent variable squared, is directly proportional to, or is proportional, maybe not directly, but proportional to the independent variable. And then we're going to use our form of the equation, y equals mx plus b, and we're going to replace our y with whatever's on our y-axis, so that's velocity squared in meters squared over seconds squared, is equal to our slope, which is, we can just make up 16. And we'll do the units on the y divided by the units on the x. So that's meters squared over seconds squared divided by meters. So one of the meters is going to cancel and we get meters per second squared. So we have 16 meters per second squared as our unit. And then we multiply by position, and that's in meters. And there is no y-intercept in this case, but there may be at some points. Another way to do this one, I'll show you the other way, is to take the square root of the x values. So you could also square root all of your x values and regraph it. So you'd have the square root of x, and the unit there is the square root of m. And then on this axis, you would just have velocity in meters per second. That would also give you a straight line. So now we can apply this again, y equals mx plus b, and our y is velocity in meters per second. Our slope is something, I'll just put 12. That's not exactly what it is, but that's 12. And then we'll figure out our unit. Now this is what I was talking about where the units get a little crazy. So we've got meters per second divided by the square root of meters. So that's kind of an ugly unit that goes in here, which is why I prefer to use this method usually. There are times where this works nicely, but not always, right? So then we multiply by our square root of x and square root of meters, and then we would add our y-intercept if we had one. So that is an introduction to linearization. What you need to know and what you need to study is that if the shape is like this, if you have a hyperbola, you're going to take the inverse of the x values and regraph it to linearize it. Or you could do the inverse of the y. Usually we do the inverse of the x. Then if you have a top opening parabola, you're going to square all of your x values. And the way that I remember that one, I think this one's pretty easy to remember because it's an inverse. The way I remember this one is that You know, in the beginning this might look kind of linear, but then it starts curving upward because these x values are growing too fast, right? And so you have to square the time to catch these up, to like bring that curve back to straight. And then you have to remember that a side opening parabola is going to be linearized by squaring the y-axis or squaring the x, but I would just focus on squaring the y. And the way I remember that is the x values here are growing faster than the y, which is why it's curving down like this and flattening out. So what you want to do is square your velocity values to get them higher, to like bring that curve back out to straight. That's just kind of how I remember it. All right, happy graphing.